Hello everyone, thank you for attending my talk. I'm Sili. I'm happy to share my topic today. My topic is trapfuzzer, coverage-guided binary fuzzing with breakpoint. First of all, please allow me to introduce myself. I am security researcher at Huawei Root Lab. I focus on software availability research. Below are my Twitter and GitHub links. The tool will be open sourced on GitHub. If you are interested, you can follow me. Next, I will show my topic. Let's start our topic. This is the outline of today's presentation. Firstly, I will introduce some background of trapfuzzer. Next, I will explain the implementation of the tool. Then I will take WPS Office as an example to explain how to fuzz software with trapfuzzer and the fuzzing result. Finally, I will summarize the speech and introduce some future plans. Now, I will introduce some background knowledge of trapfuzzer, including the concept of fuzzing as well as the comparison of developing trapfuzzer. First of all, let's take a look at what is fuzzing. The simplest fuzz is shown in the figure. The code in the figure is to generate random binary data. Then, if we feed the output data to target process, this is fuzzing. Next, I will briefly introduce coverage-guided fuzzing. The general workflow of coverage-guided fuzzer is shown in the figure. It usually maintains a queue of seed test case and performs a fuzzing loop. First, the fuzzer will select a test case and mutate it to generate a new test case. Then fuzzer will feed the new test case to target process. Unlike black box fuzzing, coverage-guided fuzzer will monitor the program execution to check its code coverage. If the test case finds new code coverage, the fuzzer will put the test case into the queue. Through this feedback mechanism, fuzzer can automatically generate efficient test cases so that fuzzer can fuzz the deep logic of the program. Next, let me introduce two main events that inspired me to develop trapfuzzer. As shown on the left side of the slide. In April 2020, Google Project Zero published a research about fuzzing image I/O on macOS system. In order to perform coverage-guided fuzzing in macOS, the author put a novel binary instrumentation method to home fuzz. It first obtains the start offset of each basic block in the program through ADA Python. Then it will patch the module in memory, which just replaces the first byte of every basic block with 0xcc. 0xcc is the breakpoint instruction on Intel. Then it will register a SIGTRAP handler to handle the breakpoint events, and finally get the basic block that has been executed. This article reminds me of a research in 2018, which is the right side of the slide. Its main idea is to obtain coverage by patching the first instruction of each basic block in file. The difference with Google Project's method is that it directly patches executable file instead of patching memory. After patching the file, it runs the target process by a custom debugger and handles the breakpoint event in it. Combining my previous fuzzing experience and this two security research, I realized that first, the existing excellent fuzzing tools such as AFL home fuzz are not perfect, and they are still unsupported or incompletely supported scenarios such as large closed-source programs and some special operating systems. Second, using relatively inefficient instrument method for fuzzing can also obtain better results than complete black box fuzzing, such as instruments with breakpoints. I also searched through Google and found that fuzzing tools for large closed-source software are rare. Commonly used Linux fuzzing tools are PeachFuzzer and AFL. They both have some shortcomings. First, PeachFuzzer don't support coverage information. Second, AFL QEMU mode is only suitable for relatively small programs, such as an image path library. So I decided to develop a fuzzer based on the breakpoint mechanism to support some scenarios that are not covered by existing tools, such as large closed-source file parsing software, and provide coverage support. Next, I will introduce the implementation of trapfuzzer, including the software architecture and the implementation of each module. First, let's take a look at the overall architecture of trapfuzzer. Trapfuzzer can be divided into 4 components, namely binary patching module, fuzzer schedule module, seed mutation module, and the trace module. The workflow of the tool is as follows. First, the user finds the modules that need being instrumented, then use binary patcher to patch the target module. It will replace the first instruction of each basic block with a breakpoint instruction. In this step, we directly patch the executable file in file system. Then, user starts the fuzzer and provides some initial test case for fuzzing. The fuzzer will randomly select a test case from the seed queue and hands it to the seed mutation module. The seed mutation module will mutate the test case to generate a new test case. Then fuzzer will feed the new test case to target program. Then the trace module starts the target process in debug mode. It will handle the breakpoint events of target process. Finally, the trace module will give the obtained coverage information to the fuzzer. The fuzzer schedule module will use this coverage information to determine whether the test case needs to be added to the queue, and at the same time, fuzzer will score the success in the queue. The above is the approximate workflow of trapfuzzer. Next, I will introduce each module in detail. First, I will introduce the implementation of the binary patching module. This page describes the working mechanism of the binary patching module. The input of binary patcher is the executable file that needs to be instrumented, such as a library. The output is the patched file and the basic block info file. The basic block info file stores each basic block information of binary file, including the virtual offset, the file offset, and the first instruction of each basic block. The workflow of this module is shown in the figure. First, the user provides some modules that need to be instrumented, such as lib.a.so, lib.b.so, libx.so. Then, the binary patcher will start multiple IDA instances to analyze these shared libraries. After the analysis is completed, it will use the IDA Python script to extract the information of each basic block and save it as a basic block info file. Finally, the binary patcher will patch this shared library according to the basic block info file. It will replace the first instruction of basic block with breakpoint instruction. Next, I will introduce some examples. And shown in the figure is an example of basic block info file. The format of the file is as follows. The first 4 bytes indicate the size of the file in the memory. Next is the file name of the executable file corresponding to the basic block info file. The file name is followed by the bbinfo structure list. The bbinfo structure list representing the information of each basic block. There are 3 members in bbinfo structure. The meaning of each member is as follows. First, RVA represents the module offset of the basic block in the process memory. FOFF represents the offset of the basic block in the file. Inst size and inst indicate the bytecode for the first instruction of the basic block. This picture shows the difference between an ELF executable file before and after being patched. The left side of the picture is the original file. The right side is the patched file. We can see that some instruction in the original file has been replaced with 0xcc, which is actually the bytecode of the breakpoint instruction. Here are 2 screenshots of IDA. The left is the original binary. The right is the binary after patch. You can see that some instructions have been replaced with int3 instruction. Next, let's take a look at the implementation of the seed mutation module. And shown in the figure, the seed mutation is to randomly replace some data in the test case. Currently, there are 2 seed mutation modules in trapfuzzer, red emsa and mutator and tiny mutator. randomemsa mutator encapsulates randomemsa. Randomemsa is an open source seed mutation tools. Tiny mutator is a relatively simple seed mutation tools, including some basic mutation strategies, such as byte flipping and boundary value replacement. Unlike a randomemsa mutator, tiny mutator supports configure the ratio of seed mutation so that the mutator will only mutate a small part of the test case. The comparison of these two mutators will be introduced later. Let's continue. On this page, I will introduce the implementation of the Fuzzer module. The Fuzzer module will first load the initial test case to seed queue and do Corpus distillation on it. Then it will traverse the seed queue, mutate the test case, and use the trace module to start the target process. Finally, it will get the coverage and execution status of the process. If new coverage is found, the new test case will be added to the seed queue. If crash is found, the crash context is saved, such as register and stack trace. There are also two simple scheduling strategies in the Fuzzer module. The score of test cases that found new coverage will increase. The score of test cases that trigger DOS vulnerabilities will decrease. The purpose of this is to further explore new coverage as much as possible and to find fewer DOS vulnerabilities, because DOS bug will waste too much time. The workflow of Corpus distillation is as follows. First, the fuzzer lets the program process each test case in the seed queue. Then only save the test case which can generate unique coverage to seed queue. In this way, we can reduce the number of test cases in the seed queue. The figure below is an example. There are 5 test cases in the initial seed queue. The basic block coveraged by these 5 test cases are A, B, C, D, E, F. The test case 1, 2, and 5 in the queue can also cover A, B, C, D, E, F. Therefore, the final test case saved in the seed queue after distillation is test case 1 to 5. Next, I will introduce the implementation of the trace module. I will first introduce the principle of trace module. Firstly, we use the binary patch to replace the first instruction of each basic block in the executable file with breakpoint instruction. Then, we use the trace module to start the program. The trace module will process the breakpoint event and record the PC register. When the breakpoint is triggered, then it will replace the breakpoint instruction with the original instruction, and then let the program continue. In this way, we can get all basic blocks that have been executed. Therefore, the trace module in trapfuzzer is actually a simple debugger. Next, I will introduce the first trace module. Its name is Python ptracer. According to the previous introduction, we know that the trace module is actually a simple debugger. Since the other modules of trapfuzzer are developed with Python, I also wanted to implement a debugger through Python. After searching, I found the Python ptrace library. Through this library, we can use the ptrace in Python. In addition, there is also a debugger demo in the code of Python ptrace library. So we can quickly implement the trace module based on the debugger demo. The workflow of the trace module is as follows. First, we use create and attach process to start the target process. Then use continue function to let the process continue, and use wait signals function to wait for the process trigger SIGTRAP signals. When the process executed a breakpoint, it will trigger the SIGTRAP signal. It means that a new basic block is executed. Then, tracer saves the current PC register and removes the breakpoint instruction. Then it let the process continue to execute. After finishing the first version of trapfuzzer, I hope to find some real programs to test it. After some searching, I found that WPS Office released a Linux version software in 2019. WPS is an office software in China that supports view and edit Word, Excel, PowerPoint, and other file formats. It supports various operating systems, including Windows, Linux, macOS, and so on. Finally, I decided to use WPS as my first fuzzing target. In the previous introduction, we know that the trapfuzzer will trace program by patching executable file with breakpoint. So we need to find the module need to be instrumented before fuzzing, which is the module responsible for passing the input file. Next, I will introduce how to quickly find the file passing modules in target software. We know that the general workflow of the file passing program is as follows. First, the program will open the file. Then it will read data from the file and pass it. Finally, it will close the file. In this process, program will call some library functions. Therefore, we can quickly find the file passing modules by hooking library functions such as file operations, and then we can check the call stacks of target library functions. On the Windows platform, we can use process monitor to trace the file operations of the target process and obtain the corresponding call stack. As shown in the figure is an execution log captured by the process monitor when WPS is passing a doc file. When we check the call stack of the read file functions, we can find that there are two DLL belong to the WPS, which are kso.dll and wpsman.dll. Read file is a Windows API for reading file data. We can infer from the log that these two libraries should be responsible for passing file data. In this way, we can find the modules that need to be instrumented. On the Windows platform, we can quickly locate the file passing module with the help of process monitor. However, there is no such easy-to-use monitor tools for Linux platform. Similar tools under the Linux platform are strace and ltrace. These tools are used to monitor system calls or library function calls, but they cannot obtain the call stack of target function, so it is not very useful for us. After some research, the best tool to get the call stack under the Linux platform is GDB, so I decided to implement a simple version of process monitor based on the GDB plugin. Its implementation is to set some breakpoints for commonly used file operation functions. Then it will check the file name after program hit the breakpoint. If the file operation is for the target file, the call stack is recorded. Let's take a brief look at the implementation of Linux version file monitor. This picture on the left is the code for hooking fopen function. Breakpoints can be set through the gdb.breakpoint class. In the stop function of breakpoint class, user can customize the breakpoint processing behavior. If the file to be opened is determined to be a DOC file, the call stack will be printed, and some information will be recorded. Then it will replace a breakpoint on the return address of the call to fopen. The purpose is to obtain the return value of fopen, which is used to filter fread, fwrite, and other function calls later. The picture on the right is the call stack of the read and fread functions when WPS is passing the doc file. In the call stack, we found that the Linux version of kso.dll and wpsman.dll, namely libwpsman.so and libkso.so. In addition, I also found libwpsio.so. In this way, we can locate the file passing module of WPS for Linux. This page shows the modules that need to be patched when WPS pass doc file on the Windows and Linux platform. On the left is Linux, on the right is Windows. When I started fuzzing, I found that Python ptrace can't trace the WPS process. After WPS was executed for a period of time, it will crash. I guess that Python ptrace may have some bug in processing multi-thread programs. After some research, I found that GDB is an excellent debugger for Linux platform, so I decided to develop the trace module based on GDB. The reasons are as follows. First, GDB has fewer bugs and can get completely core-stack of the process and supports various architectures. Second, we can use Python to develop GDB plugins. Third, GDB is open source. We can customize it as needed. Next, I will introduce the implementation of GDB Python DbgEngTracer. First, I will introduce some GDB Python API used by this tracer. Read register function is used to read register value. Read and write memory function is used to read and write process memory. Pass and eval function is used to execute GDB translation and get the results of translation. Execute function is used to execute GDB command and get the results of command execution. GDB.events.stop.connect function is used to register a GDB stop event callback function. When target process triggers a signal, it will enter the callback functions for processing. Next, I will introduce the implementation of the tracer. When the process executes the breakpoint instruction, the SIGTRAP signal will be triggered. If the breakpoint is not set by GDB, the callback function registered through GDB.events.stop.connect will be triggered. Due to the limitation of the GDB Python plugin, when GDB enters the stop callback function, the GDB process will enter its command loop, and GDB needs waiting for user input. Therefore, it is necessary to send the continue command to the stdin of GDB after it stops. Only in this way, the debugged process can continue execution after it executed a breakpoint instruction. Let's take a look at the communication between Fuzzer and the tracer. GDB Python DbgEngTracer consists of two parts. trapfuzzer.py is a Python plugin for GDB. It runs in the GDB process. GDB Python DbgEngTracer.py is responsible for interacting with GDB, including start one test and get the results of the test. It runs in Fuzzer process. First, the Fuzzer generates test case through the seed mutation module. Then it could feed the test case to the target program. Then the Fuzzer starts the GDB with trap.py. After trap.py is loaded, it will load the basic block info file and then start the process. When the process triggers a breakpoint, GDB would handle the SIGTRAP signal. It will enter the callback function registered in trap.py. The function will record the PC value at this time and then restore the original instruction at that position. Due to the limitation of the GDB plugin, the process will be suspended and GDB will wait for user input. Then Fuzzer process sending continue command to the stdin of GDB. It would let target process continue execute. Next, let's take a look at the core code of the tracer. First, take a look at the code of the GDB plugin part, which is trap.py. In the code, it first registers the stop callback function through gdb.events.stop.connect API. In the callback function, if it is a breakpoint event, function first searches basic block info file according to the PC and get the original instruction at that location. Then it removes the breakpoint instruction and records the address of the basic block. Finally, it will let the process re-execute this instruction by setting the PC register. Next, I will introduce the implementation of GDB Python DbgEngTracer. It first starts the GDB process through subprocess and load trap.py. Then it will monitor the std out of the GDB. If GDB prints received the signal SIGTRAP, it means that the process has executed a breakpoint, and trap.py has already handled the SIGTRAP signal. At this time, it will send a continue command to stdin of GDB to let the process continue to execute. And after the process is started, the script will set a timer and kill the process when the timer expires. The purpose of the timer is to detect DOS vulnerabilities. Now we have a trace module that can trace WPS. We can start fuzzing with GDB Python plugin tracer, but there are two problems that affect the fuzzing speed. The first problem is that WPS will not exit the process after passing the file, but will stay on the GUI interface and waiting for the user to operate. So the fuzzer needs to manually kill the process. Therefore, the problem is when to kill the process. The commonly used method is to set a timeout. When the timeout occurs, the fuzzer will kill the process. This approach has two disadvantages as follows. The first disadvantage is that due to the setting of timeout, the execution time for each test case is fixed. When process passes simple test case, which actually passing time is less than timeout, it will waste time. When process passes complex test case, which actually passing time is greater than timeout, it will result in an incomplete file passing. The second disadvantage is that it cannot detect DOS vulnerabilities. The following describes trapfuzzer's solution to this problem. Generally, the application will execute the same code every time when it enters the GUI loop. So if we kill the application when it enters one of the basic blocks of the GUI loop, we can avoid wasting time and ensure that the input file has been completely passed. The workflow is as follows. First, we use the trace module to trace the program execution and print the executed basic blocks. Then we can find the last basic blocks executed by the process after it enters the GUI loop. We named it end BBL. In the following fuzzing, when the process reaches end BBL, it means that the process has entered the GUI loop and the process can be killed at this time. In addition, during the fuzzer will also record the execution time of each test case, which is used to calculate the average execution time. The average execution time is used to calculate the timeout of DOS vulnerabilities. When the execution time is greater than timeout, it is considered that DOS vulnerabilities have been found. This is a video of obtaining end BBL with the trace module. It can be seen that the process will continue to execute the new basic blocks at the beginning. But when it enters the GUI loop, there are no new basic blocks being triggered. So when WPS GUI has finished rendering, the area marked red in the figure is a basic block of GUI loop. We can use it as end BBL. Next, I will introduce the second problem that greatly affects the speed of fuzzing. For large software, because the number of breakpoints is very large, it will take a lot of time for each execution. This will cause our fuzzing speed to be very slow. The following table shows the number of breakpoints that the program needs to patch. Trapfuzzer implements an accelerated mode to handle this problem. First of all, we know that in Trapfuzzer, the trace module will save and send the basic block information of each test case to the fuzzer. In the accelerated mode, the fuzzer first obtains the executed basic blocks from the trace module, then remove the breakpoints of these basic blocks in the file system. In this way, the breakpoint instruction of each basic block will only be triggered once during the entire fuzzing process, or it will never be triggered. The result is that the average execution time of the program in fuzzing is similar to the program without instrumentation. As shown in the figure, the blue rectangle in the figure represents a module being instrumented. The small yellow rectangle represents the breakpoint instruction in the module. The small white rectangle represents the original instruction in the module. The first blue box indicates that when module is instrumented, there will be a lot of breakpoint instructions in it. The second blue box indicates that some breakpoints in the module are removed after the first execution. The third blue box indicates that more breakpoints are removed after the second execution. With the running of fuzzing, there will be few and few breakpoints in the module, and the number of the breakpoints triggered by each execution will gradually decrease, so the traced process will execute at a speed closer to the original execution. Of course, there is a problem with this approach. Due to the optimization method, we can only obtain basic block coverage information because only test case that triggered new basic block can be saved during the fuzzing process, and there is no edge coverage information. But despite this, it is much better than black box fuzzing, which is without coverage guiding. After solving this problem, we can finally start fuzzing WPS. Let's take a look at a video of fuzzing WPS. During the fuzzing process, WPS will restart multiple times. During the test, GDB Python PlaginTracer will process the breakpoint event triggered by the process and send the result to the Fuzzer when process exits. Currently, we can fuzz WPS. I first fuzzed with a random mutator, but no crash was found after 3 days of fuzzing. After that, I tried to fuzz it with a tiny mutator, and I found more than 10 crashes after fuzzing in 1 day. I guess the reason may be as follows. Random mutator doesn't consider the ratio of data mutation, which directly mutates the content of the entire file. This may seriously destroy the file structure, cause the test case to be discarded very early, so that deep vulnerabilities cannot be found. Due to the mutation ratio, tiny mutator will only mutate a small part of the test case, so that most of the structure is valid. Then we can find the deep logic of the software and find more vulnerabilities. Currently, trapfuzzer can fuzz Linux software. In order to further enhance the fuzzing speed of the Linux platform and make it easy for user debugging, I developed trapfuzzer GDB Tracer by modifying the GDB source code. Next, I will introduce the implementation of this. First of all, I will introduce why I want to modify the GDB source code to develop trapfuzzer GDB Tracer. Although GDB Python PlaginTracer can meet the fuzzing requirements, there are still some shortcomings, such as, first, it is inconvenient to debug. We need to use a Python script to send continue command to the std of GDB. Second, we need to restart GDB for each test. The Python runtime, the communication of the trace module and Fuzzer will cause additional performance overhead. And the trapfuzzer GDB Tracer have following advantages. First of all, its speed will increase, and we can compile static link GDB to reduce the requirements of environment, and it is easy to debug. In order to modify GDB, we first need to understand the code of GDB. On the Linux platform, GDB uses the ptrace to debug a program. In addition, it will pass the ELF file used in the debugged process, so that a relatively complete code stack can be obtained. When GDB starts the debugged program, it will call start event loop function to start the event loop, and waiting for events from the target process, such as hitting a breakpoint, creating a child process, and so on. The following figure shows the code stack of GDB when it handles breakpoint events. Next, I will introduce how GDB processes the breakpoint events. First, GDB starts the event loop through the start event loop function. When the process reaches the breakpoint instruction, the kernel will send the SIGTRAP signal to the target process, and this time, GDB will call GDB do one event to process the event, and finally call handle inferior event to handle the event of the target process. If it is a signal event, it will enter handle signal stop. Handle signal stop function is used to handle the situation where the debugged process stops due to receiving a signal. The screenshot is the code used to handle the SIGTRAP event in the handle signal stop function. We can also use similar code to implement our tracer. Next, I will introduce the modification for GDB. We manually modify the handle signal stop function to let GDB automatically handle the breakpoint events of process. The logic of processing SIGTRAP signal after modification is as follows. First, it gets the value of the PC register, and then finds the module where the PC is located. Then, according to PC and the basic block info file, it can get the original instruction of the position. Finally, replace the breakpoint instruction with the original instruction, and let the process continue to execute. Next, I will introduce some useful GDB functions. We can use add_com function to add custom GDB commands, and use execute command to string function to execute GDB command. The screenshot is the code that trapfuzzer GDB automatically processes the SIGTRAP signal. The workflow is as follows. First, it finds the corresponding module according to the PC, and calculate the module offset. Then it removes the breakpoint instruction at this position, according to the offset and the basic block info file. Finally, it uses keepGoing function to let the process continue to run, and let GDB don't stop. Let's take a look at the interaction diagram between the tracer and the fuzzer. The main difference is that all SIGTRAP events are processed in GDB, and GDB will only be started once during the entire fuzzing process. The subsequent task control and tracer information interaction are all done through sockets. First, the fuzzer generates a new test case. Then fuzzer informs trapfuzzer GDB to start one fuzz task through the socket, and the tracer will start the target process. If a breakpoint event is triggered during the execution of target process, trapfuzzer GDB will handle it. Trapfuzzer GDB will return the execution information to fuzzer. Next, I will introduce the implementation of trapfuzzer on the Windows platform. In order to support the Windows platform, we only need to implement a Windows debugger. The best solution for developing Windows debugger with Python is winappdbg. The advantages of using winappdbg to develop a debugger is that it is developed with Python, and there are many sample codes. We can quickly develop the tracer based on these sample codes. The disadvantage is that, first, because it is developed with Python, the execution speed is relatively slow. Second, winappdbg can't obtain the complete code stack. The working mechanism of winappdbg tracer is no different with the previous tracer, which is just dealing with breakpoint events. As mentioned earlier, winappdbg has some shortcomings. By searching in Google, I found that the DbgEngine API can be used to develop Windows debugger. The DbgEngine API is a series of APIs for developing debuggers provided by Microsoft. Users only need to register the corresponding callback function to implement a debugger. The advantages of developing a debugger based on the DbgEngine API are as follows. First, because it is developed by C, the execution speed is relatively fast. Second, it can get the completely code stack of the program. Next, let's briefly introduce the code how DbgEngTracer handles breakpoints. First, in DbgEngine, you can use the write virtual and read virtual function to read and write memory of the process. And the get stack trace function is used to get the code stack of the process. The code for handle breakpoints is shown in the screenshot. The logic of the code is similar, so I won't repeat it here. Let's take a look at the demo of fuzzing Windows platform. Next, I will introduce the crash duplication scheme in the trapfuzzer. First, we get the code stack of the process when it crashes. Then, we take out the lower 12 bytes of each layer of the code stack for splicing. The result of splicing is used as the hash of the crash. When a new crash occurs, it will judge according to the hash whether the crash has been recorded before. The figure below is an example of calculating hash of the crash. When the GUI program is executed, if there is an error, it usually pops up a dialog box. Fuzzer needs to automatically handle this dialog box. The common way to solve this problem is to use Python AutoIt library to automatically process the dialog box. As shown in the figure, we can use AutoIt to search for target dialog box and then call AutoIt.control click to automatically click the button. Or we can use some existing tools such as Horon, which is a Chinese antivirus software. It carries a tool for processing the dialog box. The advantages of using Horon is that you can directly use the GUI to select the dialog box needed to be closed. Then, as long as the dialog box appears in the future, it will automatically handle it for us. The following figure shows several dialog box rules, which are used to fuzzing Microsoft Office. Here is another useful feature of trapfuzzer. Trapfuzzer will listen a management port when it started. User can connect to the management port through NC at any time to check the status of the fuzzing process, such as the number of paths found, crash information, and execution speed. Next, I will introduce the preparation for starting fuzzing and the results of fuzzing. Before we start fuzzing, we need to prepare some environments. We know that fuzzing has three important factors, which is execution speed, sample quantity, mutation algorithm. There are several command methods for obtaining samples. The details are as follows. I usually use the second and fourth methods. In order to further increase the speed, we can use RAM disk, which can speed up the I/O operation of the program. For file fuzzing, it can improve the execution speed, but you must pay attention to regular backup files, because the files in the RAM disk will no longer exist when the machine is restarted. We can use the mount command to create the RAM disk on Linux, and we can use the IM disk toolkit on Windows. My fuzzer equipment is my laptop. Its configuration is as follows. I run 2 virtual machines on it. The final fuzzing results are shown in the table. You can see that trapfuzzer have found many vulnerabilities in various software. The following is a simple comparison between trapfuzzer and other fuzzer. After comparison, we know that the advantages of trapfuzzer is that it is relatively simple to use and can support coverage. Here I will summarize my speech. First, Sili is important and mutation ratio is also important. Second, the GDB and debug engine API is very nice. Third, fuzzing with break coverage is much better than now. There are some future plans. First, support more architecture such as ARM MIPS. Second, optimize the distributed fuzzing scheduling. Third, automatically detect data mutation ratio and mutation range. Fourth, more precise crash duplication mechanism, and so on. Thank you everyone. The above is all my speech.